I'm Roberto Tron, assistant professor in mechanical engineering. And today I'm going to talk about a project which is related to what Yanis talked about. We are on the same grant. And the problem I'm looking at is autonomous navigation. And I think about autonomous navigation as learning, the robot learns how to navigate in a way that you really don't have to think about it. It's very fast, it's easy to implement, and it's very robust. So if something changes in the environment, like Christos was saying, you should still be able to navigate. At least humans and animals can do it. So the standard approach in robotics, so this is a problem that has been studied in robotics for 50 years. The typical solution is give you just a single reference path. So you plan your path through the environment and then you follow it. The problem is that then robots are imperfect, so they cannot follow this path exactly. So you need to put a low-level controller on top of it that if it deviates, then it brings you back to that controller. But if there is like a large deviation, like somebody takes up the robot and put it somewhere else, then either you need to replan online, which can take a lot of time, or you need to take a suboptimal solution that go back to the original path and then follows it. What we are doing, my group, instead is to, instead of looking at singular paths, we look at entire feedback controllers. So we assume that the robot sees some landmarks in the environment and then decides what to do based on those landmarks that it sees. And the advantage of this is that instead of manipulating single paths, reasoning over single paths, we reason about entire control field. So not just follow a single trajectory, but simultaneously everywhere, anywhere the robot is, will know what to do after planning. And the nice thing about this is that it's very easy to implement. It's just a linear control. And you can find the solution through linear programming. So it's very fast to find the solution. And the nice thing is that you go through the linear programming, the formulation can take a little bit, but then online you just apply this control law, this feedback control law. So it's very fast, easy to implement. And in practice, I was rather surprised because my student could make these experiments work in a week before the deadline of the paper. Usually that doesn't happen. But the nice thing is so that on the left is like we plan the trajectory in the environment that we plan. But then we try to confuse the robot and we change the environment. And but the interesting thing is that if also the landmarks change in the same way the environment has changed, without replanning anything, the robot automatically adapts to the new environment. So we're successful even if we are robust even if we change the structure of the environment. And more closer to the BioInspire team that Yanis was talked briefly about, we are trying to use the same theory to explain what neuroscientists have been looking in the brain. So neuroscience models are sort of handcrafted. Neuroscientists have made the models and then saw that more or less they will represent what they actually happening in the brain. So for instance, if you are on a car and we're going through a street, one thing that the brain does is keeping track from images what your current speed, so that you don't want to go too fast or too slow. And how this is done at a very high level is that there are some simple cells that from these images, they give you some estimate of the current speed, but it's very noisy. And so then there are more complex cells that filter these estimate and give you something which is much more robust. And it turns out, I don't have time to explain this how, but it turns out that the same theory that we used before also applies into designing these filters that give these nice robust properties. And that's all.